So now what we're going to do is we're going to show an example application of a pair of Java condition objects. And to be consistent with what we covered before, we're going to look at this in the context of the array blocking queue. Remember, array blocking queue is a blocking bounded FIFO queue, and it's part of the Java class library. It's actually a very helpful class and is very commonly used for various types of message passing operations. There's also a link blocking queue implementation, but its implementation is a bit different from what we're going to cover here, so we won't talk about it right now. Under the hood, the array blocking queue extends abstract queue, which is an implementation of the blocking queue interface that provides a bunch of methods that are shared between array blocking queue and link blocking queue. So it's basically about refactoring and enhancing code reuse. We're going to look both at the interface and the implementation of array blocking queue. Now, we've looked at this a bit before when we talked about reentrant lock. And if you think about what we covered then, we discussed how array blocking queue is implemented internally using a dynamically sized array. And this array is created by the constructor, and it could be whatever size is necessary, but once it's created, it doesn't resize itself. There's a bunch of fields that are part of the array blocking queue class, and these fields are going to be protected by the reentrant lock, which we talked about before, in order to prevent race conditions. And this reentrant lock is also used in order to help synchronize the condition objects we're about to talk about. So the state we're doing here is basically used to coordinate the put and take calls. So we have obviously the items, which is the elements in the array blocking queue. We've got two indices, take index and put index, that keeps track of where the next take and put are going to go in the items array, respectively. And then we also have another field that keeps track of the number of elements that are currently in the queue. Now, last time we've talked about this particular class, we only focused on the reentrant lock. And so in this particular case, we use the reentrant lock in order to protect the state of the class, which we just looked at, from race conditions. And so I'm assuming that you're familiar with that, or if you need a refresher, just go back and watch the application example for reentrant lock. What we're going to focus on now, of course, will be the use of two condition objects, one called notEmpty and the other called notFull. And as the name implies, notEmpty is used by threads that are trying to take something from a queue when it's empty, and notFull will be used by threads that are trying to put something into a queue when it is full. And we separate these things out into two different conditions, or two different condition objects, to be able to reduce redundant wake-ups and redundant checking. And we'll talk more about this when we get into the usage considerations part of our lesson later. Here's the constructor for array blocking queue. As you can see, it takes in a capacity, which is just indicating how big to make the array of objects. And notice that even though the array blocking queue is a generic class, it stores things as objects. And that just happens to do with some of the weird quirks of Java's generic mechanism called type erasure. I won't go into that in detail now, but if you're curious, look up Java generic type erasure, and it's pretty weird, but whatever. There's also another parameter here called fair, and much like for the things we talked about when we discussed reentrant locks and the semantics of semaphores and so on, fair can be used to control the order in which a group of threads can call the methods on the queue. And so you can either have fair or non-fair semantics for your reentrant lock. So that all depends on what parameter you pass in. As a general rule, you're better off to make things not fair because it'll be more efficient. So if you set the parameter to fair, then threads will block in FIFO order on the reentrant lock. Whereas if you use false, then the order in which things are accessed is unspecified. And that's usually what you want to do if you possibly can, because it's going to be a lot more efficient. Both of these condition objects share that common reentrant lock that's returned, that's initialized here. And when you say lock.newCondition, it'll return a new condition object that will be associated with that lock. So you can see we make ourselves a new condition that's the notEmpty condition, and we make a new condition that's the notFull condition. So now that I've kind of given you a quick overview of condition object, let's take a look and see how you can visualize its usage in practice in the context of the array blocking queue. So you're going to see two things here. The left-hand part of your screen facing you when you look at the screen will be a visualization of what's happening using kind of a cool little mechanism. And then the other side, the right-hand side of the screen, will be the code that's causing the left-hand side of the screen to look the way in which we're visualizing it. And of course, what's really being shown here, the key thing to realize what's being shown here is the so-called monitor object pattern. And this is a pattern from the POSA 2 book. You can also see it at the link below. And it synchronizes method execution to ensure that only one method runs in an object at a time. And it allows an object's methods to be cooperatively scheduled between multiple threads in order to make sure that they execute in the right order, under the right conditions, at the right time, and so on. So when we start out here, you can see that we have our array blocking queue object, which has a lock, which will be used to mediate access into the critical section, and a pair of condition objects, not empty and not full. And so let's take a look at how this is all going to work out as we talk about different use cases. So we'll first start by allocating an array blocking queue that has 10 items in it. It'll be 10 strings in this case. And that's the code on the right-hand side leads to what you see on the left-hand side. So a thread comes along and it's thread T1, and it's going to call the take method on the queue. Now, this take method has to block because the queue starts out being initially empty. So here's what it looks like. If you were to take a look at the take implementation from the Java class library, you'd see that take starts out by essentially getting into the critical section by calling lock interruptibly on the lock. And since there's nobody else there, it gets right in. And now the lock is in use. It's been acquired. And then we use the guarded suspension pattern, which we talked about in an earlier lesson. And what this will do is this will say, while the count equals 0, in other words, while there's nothing in the queue, go ahead and call await on the not empty condition. And when you call await on the not empty condition, this atomically blocks thread T1 and releases the lock. So if you take a look at the visualization here, we're running at this point. If the count equals 0, then we go ahead and block. And that kind of moves us out of the critical section. So we're now going to be parked in the not empty condition waiting room. I like to think about it like a waiting room. And as you can see in this particular case, that will put the thread to sleep and atomically release the lock. So the lock is now available for someone else. So let's go ahead and take a look at that something else. So in this case, let's assume that thread T1 is blocked, waiting on not empty condition. And now another thread comes along. This will be thread T2. It will also have started out with the same instance of the queue with the same value because it was shared between those two threads. And what it's going to do is it's going to make a new string and then try to put it into the queue. So thread T2 will try to put the new string into the queue, which is currently empty, has a thread T1 waiting on the non-empty condition, and the lock is available. So when put is called, thread T2 enters the monitor object, and then it will be able to successfully acquire the lock because there's no contention because it was released by thread T1. That's why await has to put the thread to sleep and release the lock so we don't end up with some pathological deadlock condition. And at this point, then it will also use the guarded suspension pattern. The difference, of course, in this case will be that the count will be equal to 0. So this while loop, in fact, will essentially not have to be used. The condition will not be satisfied, or rather the condition we're looking at here will not be satisfied. And so we're going to actually go ahead and put something into the queue. So we didn't have to block because the queue was not full, because of course the queue is empty. So at that case, we go ahead and call the insert method for the element we're trying to put into the queue. And here's what insert does. You can see that insert is not synchronized since it must be called with the lock held. So if you take a look up here, you can see that the lock is held when insert is called. Insert itself doesn't have to reacquire the lock. And that's actually something that's called the thread safe interface pattern. And if you take a look at the thread safe interface pattern from the POSA 2 book, or at the link below, you'll learn about this particular way of designing classes that are monitor objects that are efficient. So what insert does is it puts the element at the next free index in the items array, increments the index by 1, possibly wrapping it around if it gets greater than the size of the array, increments the count by 1. And oh, by the way, all that stuff is done with the lock held because it was held when put was originally called. And then the last thing that happens is on the way out of insert, the method calls signal on the not empty condition, indicating to any threads that are waiting or a thread that's waiting that it might be possible for that thread to make forward progress because now there is something that's actually in the array blocking queue. The last thing that'll happen for thread T2 is it will go ahead and call onLock in order to release the lock and exit the critical section. And so at that point, we're done and we leave. And notice, of course, how we do this in the try finally block using the scoped locking idiom. So this is just classic use of lock and unlock with try finally using the scoped locking idiom that's also in the POSA 2 book. And we've discussed before in various contexts related to reentrant lock. So yet another reason to get in the habit of always using try finally when you're writing your code. So now that thread T1 has been awakened by thread T2, because thread T2 put something into the queue, let's see what happens. So remember, thread T1 was waiting. It was blocked in the waiting room, the not empty condition waiting room. And at this point, when it's signaled, it will wake up. This is all inside the await call, of course. Await will reacquire the lock that's associated with that not empty condition, and then it'll go ahead and re-enter the critical section. And so before await actually returns, before it lets you loop back around again, for example, the lock will be acquired. So it'll wake up and reacquire the lock atomically. At that point, it will then recheck the condition to see whether or not count is 0. Now, count could be 0 even though someone has been signaled. So even though thread T2 signaled thread T1 that it had put something in the queue, thread T3 might have come along before thread T2 was able to reawaken and reclaim that lock, and thread T3 could come zipping by, grab the lock, get the item, and go on its merry way. So in that case, thread T1 would have found there was in fact nothing in the queue, so it would have to go back to sleep again. So we still have to check that condition in a loop. And that's why we typically check those conditions in loops, because something may have come along and stolen our resource before we had a chance to wake up and grab it. Assuming that the condition is actually satisfied, in other words, the count is greater than 0, we're going to call the extract method. And here's what extract does. It also assumes that the monitor lock is held using the thread safe interface pattern we talked about before. It goes ahead and grabs the item. So it gets the item that's the take indexed item into the items array. And then it goes ahead and sets the current item to null for garbage collection purposes, increments the take index by 1, potentially wrapping it around, and decrements the count by 1 because we're taking something out of the array blocking queue. Then the last thing this code does is it signals the not full condition. And the not full condition is, of course, used if threads are waiting to enqueue something on a queue that's full. And now that we've taken something out of there, the queue may no longer be full. So we signal anybody who's waiting, so someone should wake up and see if they can make forward progress. Then we return the item, and as you can see here, that will be returned as the return value from that try block. And because we have a finally block, that will guarantee to always unlock the lock. So even though we're returning from the try block, the finally block will make sure that the lock is always released. And then we go ahead and exit the monitor and we're done. Now, you've no doubt noticed that there's a lot of moving parts here, and that's what makes things complicated with condition objects. There's a bunch of things. There's these locks, the monitor lock, for example, like our reentrant lock here. There's your conditions. You may have more than one. In our case, we have not full and not empty. So those are complicated. And so they're also coordinating each other and deciding who gets to go next. So there's a lot of coordination and a lot of mutual exclusion and a lot of moving parts. And that's what makes it tricky to understand the behavior. The good news is it's very idiomatic. And once you understand the kind of the pattern here or the sequence, it's basically kind of paint by numbers. So that's the end of our example application showing how to use a pair of Java condition objects in order to implement the Java ArrayBlockingQueue. And that's code straight out of the Java class library. So this is production Java code, and we're looking at the ways in which these features are used to implement something that really applies in practice.